I'll break it down a little bit more in the beginning, the different algebra steps that I'm doing. And as we go through, we'll get less and less. This is the algebra, more of the, this is just purely the chemistry. Anyway, so we're in chapter 2 today. We're going to start in chapter 2. A couple of things. Section 1 is units and measurements. Units. Units are very, 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 very important. Okay. If you're doing a chemistry problem and your answer is 12.38, okay? Well, 12.38 what? Because that makes a difference. It makes a difference. So we need to say what we are dealing with. Now, I'm not super strict about it, but if you go to college and have to take a chemistry class, there are definitely chemistry professors that if you get the right number but don't put a unit on, guess what? You got it wrong. Because you didn't specify what that is. Okay? Like I said, I'm not overly strict about that, but it's something to keep in mind. You want to be fully correct. Make sure you put your units on. I typically don't take points away, as long as, if the answer was 12.38 grams, and you just put 12.38, you're probably going to get 4 points. So, but we should put grams in there. Now, the other nice thing about units allow us to check our work. Okay? If you're going along and you're keeping all of your units as you're moving through the work, if you get to the end and your answer is 12.38 grams, okay, but the question asked for volume, well, you've probably done something wrong. Okay? But if you get there and you've got grams and the question asks for mass, okay, that's a good sign. Right? So it's important to keep your units, and they will allow you to double check that you've done things correctly. So now, speaking of units, those of you who grew up in the United States, I'm sorry. The units you are stuck with in the United States are terrible. Absolutely terrible. Okay? Why are we stuck? Because United States citizens are stubborn and unwilling to learn a new system, even though it's superior. That's really what it comes down to. Yeah. It's just, they're stupid. I mean, that's really all it comes down to. They are stupid. So for science, we use the SI system. It is the International System of Units, abbreviated SI, because the organization that sets these standards is based in France. And so in French, the order of words is a little bit different. And so it's SI instead of IS. Anyway, we do have a poster on the wall over here of SI units. Okay. Those Units are also in your book on page 33, those base units. Okay. So if you're not in class, look at the book. If you're sitting here in the classroom, we've got a lovely poster with it there. Okay. There are the different things. So length, we use meter. Okay. This is a meter. For those of you who are in the US, this is a little bit over 3 feet. So for mass, we use kilogram. Now remember, mass and weight are not actually the same thing. I'm not going to get too nitpicky about it, but mass is different than weight. For time, well, luckily there's really not different time standards around the world. That would make it really confusing. But the SI unit for time is seconds. Electric current is the ampere, sometimes abbreviated as amps, if you're running 12 amps through a system. Okay. Thermodynamic temperature is Kelvin. Okay. Kelvin. Now, Kelvin is interesting. Kelvin has the same magnitude as Celsius. Okay. So if you go from 0 to 1 degrees Celsius, okay, that change is the same change in temperature from 0 to 1 Kelvin. The difference is we set 0 Kelvin at the absolute lowest temperature anything can be. Okay. There are some times in some of the units that we do where if you're dealing with a negative temperature, the math just doesn't work. And so as scientists, we said, okay, let's make 0 be the absolute coldest it can ever be and get rid of negative temperatures. Okay. So it's really easy to change back and forth between Celsius and Kelvin. Celsius is, well, 0 degrees Celsius is where water freezes, and that is 273.15 Kelvin. For most of the math that we do, you don't have to worry about the 0.15, you just do 273. Okay. So, take Celsius, add 273, that gives you Kelvin. Okay, it's not too bad. The amount of a substance, our SI unit is the mole, which, if you've never taken chemistry before, that might sound funny. It is what it is. You will become very, very familiar with the concept of mole throughout this class. And then the last one, luminous intensity, the candela. We will never, ever, ever, ever use that in this class. So don't worry about it. We also have some derived units. Those are basically combinations of the base units. For example, force. Okay, force we measure in newtons. Because having a newton is easier than meter, kilograms per second squared. Okay, they're the same thing. We've just said whenever you have this, it equals 1 newton. Okay, so you can see all the different derived units. Celsius is actually a derived unit because we take our base unit, we add 273. Okay, so it's a derived unit. So, okay. We also need to be familiar with the prefixes. These are also on page 33. So the base unit for length is a meter, but often what we will measure at least bigger distances in is kilometers. So we have our base unit there, but we put this prefix on it. Now, when you are familiar with the metric system or just the SI prefixes, these come pretty quick, you know, when you figure out what they mean. That means 1,000. So 1 kilometer is the same as 1,000 meters. Okay. You're probably familiar with a couple of these prefixes already, thanks to technology. Giga, okay? If you have a gigabyte, that is a billion individual bytes. Okay? If your laptop has a terabyte, that is a trillion individual bytes. Okay? That's where those prefixes come from. That is not an exhaustive list. There are prefixes on either side of that. We just don't use them. If you're using prefixes beyond that, you're in a fairly specialized branch of science. Okay. All right. One thing that I will point out, density. Density it's not a derived unit up there because it doesn't have its own special unit, but your book does talk about it a little bit. And it's important that we understand the concept of density. Density is mass per unit volume. And if we look at this, okay? So here we have several different objects. Okay. So we have this larger piece of wood. Okay. And then we have this, I believe this one is actually copper. So which one has the greater volume? Volume? Oh, no, wood. This one's bigger, right? Okay, so this one has the bigger volume. This one has a smaller volume, but it has a larger mass. Which we pull out the electron here, we can prove. Okay, so we put this one on there. So that's 5 grams. Put this one on here. That one is 45 grams. Okay. So because this has a larger mass in a smaller volume, it has a higher density. Okay. Basically, what that means is there's more stuff packed in here. There's more stuff. So just want to make sure everyone is familiar with that because we will use the term density. That. Also, so density. So that's our math equation. You probably have to do that math at some point. But yeah, it's a pretty straightforward equation. Density equals take total mass divided by the volume. Okay. All right. So what I really wanted to focus on today, though, is section 2 in chapter 2. Okay. Because as we go through these units, we'll repeat them and we will go over them so that you become more and more familiar with them if you are not already familiar with them. Okay. Section 2, scientific notation and dimensional analysis. Now, I'm sure at this point in your math classes, you have been exposed to scientific notation. So if we have that number right there, we don't want to have to write all of those zeros, right? It's kind of tiresome. So we have this scientific notation. In this class, we will deal with very small numbers and very large numbers. Scientific notation makes them easier to deal with, okay? You guys all familiar with how to put that in scientific notation? You're close.
No, zero.
So basically what we're going to do, we're going to find the non-zero number here. Okay. Now we're going to move the decimal until it's to the other other side. So 3.85, and then we're going to multiply by 10, and we moved it 1, 2, 3, 4 places to the right. So if it's moving to the right, it's -4. And really what happens is we have 3.85, and it acts like a math equation. So times, if you put 10 to the -4th in there, you get that. And if you put that in your calculator, you're going to get that. It makes it easier to work with, especially because one of the numbers that you are going to be using all the time you don't want to have to write all those zeros. Okay? You don't want to have to do that. So this makes it much, much easier. We'll get into that number. It will get to the point where you will most likely have that number memorized. Speaking of memorization, on tests, I give you equations and constants like that. Okay? I'm much more concerned that you know how to use them than that you can memorize a bunch of numbers. Okay? So don't stress about memorizing things like that. Before the first test, I will give you a copy of the cover sheet that has all the information so that you can say, okay, I don't need to memorize this. What do I want to focus on studying? Okay, so I'll make sure you have that information. You'll know what we have. Anyway, so going backwards, going to the right, it's a negative. We have this number, okay, we can write that as 6.8325 times 10, and 1, 2, 3, 4. This time we're moving to the left, so it's positive. Okay. Now this doesn't save us a whole lot. Mostly we want to do this if we have a bunch of zeros that we need to get rid of. Okay. Okay.
So what are we going to use for the equation?
Yes, there are several instances where we're going to need to use this because we deal with really big or really small numbers. So, now, I did say that I recommend having at least a scientific calculator, because if you have a scientific calculator, odds are it has a button on here that will put this number in for you. Okay. A lot of times it's marked with an E or an EE. Okay. If you are not sure about your calculator, no, not that one. If you're not sure about it, you can bring your calculator to me and I'll tell you whether or not it has a function like that. Like I said, I recommend having a scientific calculator. It's going to make your life easier. Okay, they're really not that expensive. You can pick them up for probably $10. Okay. Yeah. So anyway, and the reason why I say that is because if you're putting this in your calculator as multiplication, it's going to get the order of operations wrong. Okay? You have to specify to your calculator that this is one number and not a math problem. Okay? Now, if you have a calculator that does not have scientific notation, it is possible to do this math. Okay? It goes through all of the rules on page 42 and 43. We're not going to take the time to go through all those rules because, like I said, I recommend having a calculator that can do it by itself. It's really not that hard. It's just kind of an extra step. You also, if you have parentheses, if you get your parentheses right, then you can put it in like that because it treats it like one number inside the parentheses. But like I said, the easiest way to do it is have a calculator that understands scientific notation. Okay. But yeah, like I said, once you have the calculator that you're going to be using for this class, because there's a lot of math and you don't want to have to do it by hand. So if you're not sure whether or not you have that function, bring it to me and I should be able to find out. So, okay, instead of working on this, because I think you guys have seen it before in math, and then when we kind of reviewed it, it seemed like most of you, it clicked again. And you said, oh, okay, yeah, I know what you're talking about. We want to focus today on what your book calls dimensional analysis, what Saxon Math calls unit multipliers. Unit multipliers. Here's the thing. Unit multipliers are incredibly useful. And once you get comfortable with them, I hope you won't hate them quite as much. In the end, the whole point of dimensional analysis is to change units. Okay? This is why Saxon calls it unit multiplier, because you're multiplying by something to change the units. As long as you are multiplying by something that is equivalent to 1, you can multiply by anything you want. Okay? So if we say, let's just do a fairly straightforward one here. We have a distance of 100 meters. Now we want to convert that into kilometers. Okay? So this is how I set them up. And I'll show you exactly what this does here in just a little bit. Saxon has you set them up in individual things, I believe. So, but I do it this way, and I'll tell you why this problem doesn't illustrate it quite as well, but we'll get to one where it's useful. So we have to remember multiply by 1, right? But in different units. Now we want to get to kilometers. So we put that unit right there. What is the equivalent of 1 kilometer in meters? Well, it's 1,000. Okay. So here, these two things, top and bottom, are the same. Okay? They are different units, but they're the same. 1,000 meters is equal to 1 kilometer. Now, anytime we have a unit that's on the top and the bottom, they cancel out. They cancel out because if you have something divided by itself, that equals 1. When you multiply by 1 or divide by 1, it doesn't change anything. Okay? In this situation, what we're going to do, we're going to take the top and multiply everything. So 100 times 1, that's easy. And then we take everything across the bottom. Now there's nothing here because this is our starting point. We take 1,000, we multiply it across the whole thing, and we just end up with 1,000. So we take 100 divided by 1,000, that equals 0.1, and then we find our units that are left, 3 kilometers. Okay. Now that one is pretty straightforward. I bet some of you who are comfortable with the metric system did that math in your head without even having to think about it. Okay, 100 meters, 0.1 kilometers. Not a big deal. But if we, for example, let's see. I'm trying to find a good example here. I don't like any of those examples. Oh, here we go. Forgot I was going to do this example anyway. It's the end of the day. Okay, example problem 4. This is 46. Now, I'll just take a moment here to point out, as we go through this class, we are going to do a lot of these example problems in the book. The example problems are great because they break it down step by step and they show you exactly how to solve these problems. If you are ever doing the homework and you've forgotten what we did in class, go to this example problem. There's almost always an example problem that is very similar to the homework. It will break it down for you so that you can get an idea of what you need to do for the homework. Okay? So we're going to look at number 4, which is on page 46, using conversion factors. So in ancient Egypt, small distances were measured in Egyptian cubits. An Egyptian cubit was equal to 7 palms, and 1 palm was equal to 4 fingers. Okay? So the ancient Egyptians had a stupid measuring system just like the United States. Okay? Now, it says 1 finger is equal to 18.75 millimeters. 1 finger, 18.75 millimeters. The other conversion factors it gave us, okay? So 1 cubit, well, obviously it's 7 palms. Okay? 1 palm is equal to 4 fingers. Okay. All right. So the problem asks us to convert 6 Egyptian cubits into meters. Okay, so this is why I set up the problem the way I do. Okay, because we can get it all taken care of in one step instead of a whole bunch of different ones. So we start with what we know. 6 qubits. Okay. So we put that right there. So we go to our conversion factors here. So we know that 1 qubit is equal to 7 palms. So that's going to be our next thing here, because that's 1. They're the same. It's the same thing as saying 1 kilometer is 1,000 meters. They're the same thing. The hardest part is deciding what are you going to put on top and what are you going to put on the bottom. Okay. The one you need to get rid of, put on the bottom. Because remember, if we put qubit down here, it cancels out. So 1 qubit is equal to 7 palms. Now, if we stopped and did that math right there, we would now know how many palms are in 6 qubits. But that's not what the problem asked for. The problem asked for meters. So we're going to add another step on. Palms. We know that 1 palm is 4 fingers. So once again, we put palm on the bottom because we need to get rid of it. And we have 4 fingers. If we stop there, we know how many fingers are in 6 qubits, but that's not what we want. We go back, we have 1 finger is 18.75 millimeters. Okay. So now we've gone using our conversion factors from the Egyptian qubit into the metric system millimeters. Okay. But that's not quite what we need. Okay. We want meters. So how many millimeters? So how many millimeters are in a meter? 1,000. So now millimeters are gone. Okay. So now we can break out our calculator and we can do all of this. So we take 6 times 7 times 4. Now, you really probably shouldn't need a calculator to do that. But then once you get to 18.75, that's okay. So that tells us that on top, once we multiply all 5 of these numbers, we get 3,150. Now this one's easy because it's 1 times 1 times 1 times 1,000. Okay. Now, if you're comfortable moving decimals, you just do that or put it in your calculator. All right. You get 3.15. You come back here, the only units that are left, meters. Okay. So, dimensional analysis. It's one of those things where once you look at it and it makes sense to you, it's going to be, you know, it just makes sense. You think, oh yeah, obviously. It may take you a minute to really get comfortable with this, and that's okay. Especially if you've never seen it set up this way that I do it. But like I said, this is how I'm going to be doing it on the board because I like that I can do the whole thing at once instead of going to my calculator a bunch of different times. Okay. But obviously, let's try it again just to make sure everyone is on board. Okay. Now, underneath these example problems, we almost always have practice problems. Okay. Sometimes I'll have you do these on your own. Sometimes we'll work them together. This kind of depends. Since this is something, you know, that you may not have seen, at least for a while, and probably haven't seen exactly the way I do it, let's work this next one together. So this is still on page 46, practice problem 21. The speedometer at right, so they have a picture there, displays a car's speed in miles per hour. Okay, what is the car speed in kilometers per hour? Okay, so we have, what did you say? Is that 65 miles per hour? It is very small.
Let's try
About
67.
67.
Let's see. You know what? Doesn't matter. We'll do the math and we'll figure it out. So we'll just assume that it's 65. Okay. Now, in this case, our first one breaks the units. Okay. So 65 miles in 1 hour. That's what miles per hour means. Okay. You travel 65 miles in 1 hour. Okay. So it gives us this information that 1 kilometer equals 0.62 miles. Okay. So 1 kilometer, 0.62 miles. Now remember, I put the miles on the bottom because we need to get rid of miles. At this point, our units are kilometers per hour. Yay, that's what we need. Okay. So we take 65 times 1 times 0.62. Okay. Go to our calculator. 65 divided by 0.62. And we get 5 kilometers per hour. Okay. It won't always only be 1 step. Sometimes it'll be more steps. Sometimes it will be 1 step. Okay. Let's see how you're doing. Why don't you give Why don't you give 22 a try? Okay. How many seconds are in 24 hours? Okay. Now you can probably do this without doing dimensional analysis, but why don't you set it up, see if you can get it with the dimensional analysis.
Wait, which one is it?
22, how many seconds are in 24 hours? I would start with 24 hours and work backwards to seconds.
We go hours.
So start with 24 hours. Have a conversion factor that uses hours. And see if you can work back to seconds. We'll do it together after everyone's had a little bit of a chance. So.
Just the right case, check mine real quick, and see if I can get it right.
Yep.
I don't think I can this one.
You guys ready to go over it?
Yeah,
Okay.
I found that.
I just don't know how to know what is going
Good. So the problem says, how many seconds are in 24 hours? What you're given is 24 hours. And we want to work backwards to seconds. Okay. Now, this is a couple steps that we need to go through. The first thing that we're going to recognize is that 1 hour is 60 minutes. Okay. So if we put 1 hour here and 60 minutes there.
Wait, why is it on? Why did you decide to put 1 hour on the bottom?
Because hours are right here and we need to get rid of it.
Oh.
Okay. That's how you choose. And it's like I said at the beginning, with dimensional analysis, the hardest part is what goes on top and bottom. Okay? But your rule is whatever you're trying to get rid of goes on the bottom. Okay? So now we're in minutes. That'll tell us how many minutes are in 24 hours, but that's not what we wanted. So we understand that 1 minute is 60 seconds. So now we want to get rid of minutes. So we put 1 down here and then 60 seconds right there. So now the only units that we're left with are seconds, which is exactly what we want. Does that make sense?
Mhm.
Yes, no?
Yeah.
Maybe.
Okay. So you get where these come from, right?
Yeah.
So we're starting with 24 hours. Our first step, we can't go straight from hours to seconds. Okay? So we say, well, how many minutes are in an hour? Okay. So we take this, 60 minutes is 1 hour. That is the same thing. 60 minutes is the same length of time as 1 hour. So we can multiply this by this, and it doesn't change what the actual value is. It just changes units. Does that make sense? Okay. But since we didn't want minutes, we wanted seconds, we're adding a second unit multiplier on there. And we're going to do them all at once. Okay. Now you could, and I believe even the book kind of breaks this down a little bit, sometimes like this, and I think Saxon probably does too. You could say 24 hours times 60 minutes in 1 hour, and you get a number. And then you would say, okay, this is minutes, but we want seconds, so we would say 60 seconds in 1 minute. Okay, and then minutes would cancel out, and you would get a new number of seconds. When we do it this way, all we have to do is, or we can do all the multiplication and division in one shot. So we take 24 times 60 times 60. That is what, 86,400? Is that what it is? 86,400 seconds.
I'm gonna go back to that 846.
Yeah, maybe. Okay. So hopefully that makes sense to you. If you're struggling with it, you can come talk to me. We'll do some more examples, things like that. But for now, I'm going to give you the last 12 minutes or so to start on some homework. Okay. First real homework assignment of the day of the year. So this is on page 62 at the end of chapter 2. This is pretty much like what we've gone over today. There's some scientific notation. There's some dimensional analysis, things like that. Okay. So like I said, page 62, the numbers are going to be 59, 67, 76, 79, 80, 81, and 84. That is on LMS. You can see it there. But yeah, so I'll give you the last bit of class. You can get started on that. Whatever you don't finish, finish for Monday.